Thank you all. Good evening and good morning. And looks like for a person from Japan, it is actually middle of the night. Thank you all for joining this. The today's the webinar. We can call it also like the 3 hours workshop, and we are going to have 3 sessions today. The first one is going to be overview of Xscale solutions, especially one who can do with the distributed deep learning, how this could be done and all. This is going to be an interesting session by the Xscale team as well as the Ohio State University team. And the second session is going to be from KLE, where the Professor Satyandan Chakur is going to be demonstrating the chip design related the demo as well as the case study and some of the open power features. That is also a very interesting session. Do pay attention to it. And then the third one is going to be from NIE and also the IBM champion, Professor Abhinandan. He's going to be sharing some of the edge application concepts and implementation techniques. Overall, we have end-to-end, the HPC, AI, and the chip design kind of a complete, the chip to solution kind of a workshop today. At the end of the session, we will also, ask you to answer some of the questions, and we will select the best students, to award them to. Be proactive on, attending the session as well as understanding the concept and answer the questions at the end of the session, through our Google Sheet. With this, I'd like to introduce Dr. Ari Subramoni from Ohio State as well as from the Xscale Solutions team to present about the overview of Xscale solution, the distributed deep learning kind of, the powerful library, which could help to reduce the training time of your, the deep learning model. Mr. Ari, please go ahead and start your presentation.
Thank you for that kind introduction, Ganeshan. Good morning, good evening, and for folks around the world, thanks for staying up late in the night and joining our session. I appreciate it. So in this talk, I'll be giving a brief overview of Xscale Solutions, our products and services, who we are, what we do, and things like that. So I know we are kind of spread all around the world geographically. I can keep talking about this for hours on end, no problems. But in order to keep the session interesting, it would help if you could ask questions. Hey, I don't get this. No, what are you talking about? So if you could keep this a dialogue rather than a monologue, it would be really, really useful. Okay, it would probably make the session more interesting for you and for me as well. So with that, let me try to let's say talk a bit about Xscale. So we are basically an offshoot of or like a spin-off from the network-based computing laboratory at the Ohio State University. So this was founded by Dr. Panda, who is a professor and university distinguished scholar at OSU. So the lab performs research and like R&D activities for high-performance computing, deep learning, and big data. And these are some of our flagship projects. And one of our most popular, let's say, development efforts is what is called the MVAPitch project. So this has been going for over 2 decades, and it's being used by a lot of organizations all around the world, like in about 89 countries, and it is powering some of the top supercomputing systems in the world. So for more details, please visit our website, and we have a lot of projects as part of our group. Now, a brief word about MVAPitch. So we are a derivative of MPitch from the Argonne National Labs. And what we do is we took MPitch and we try to enhance a lot of communication primitives. Now, let's say, let me give you like a 2-minute summary for what MPI is for those of you who don't know. So if you look at distributed programming, so what do we do in distributed programming? We try to take a big problem, chunk it up into smaller pieces, give it to separate processors to solve. Okay. Now, there are one very popular method of distributed programming is what is called as, let's say, distributed memory model, where each process is aware that there are multiple processes participating in this problem-solving endeavor, and I have to explicitly send and receive messages between them. Okay. So one very popular implementation of the distributed memory paradigm is called the message passing interface, or MPI. And MVAPIC is a very high performance implementation of MPI. Now, because you have explicit message passing, you need a lot of primitives to enable this. So MVAPIC basically implements and optimizes these primitives for different kind of emerging internode and intranode technologies that vendors like Intel, NVIDIA, Mellanox, Cornelis, all of those guys produce, like IBM or OpenPower. Like for instance, the NVLink support, the CAPI support, all of those are linked to the IBM's ecosystem. So what we do is we try to see how we can link the higher level applications which use the distributed memory model to the lower level hardware by using high performance and scalable solutions. With that, so let me give a brief overview of how Xscale solutions came into picture. So the overall goal was to bring innovative and efficient end-to-end solutions, services, support, and training to our customers. So we provide commercial support and training for state-of-the-art communication libraries like MVAPIC2, the big data libraries, the deep learning libraries. And we also provide commercial support like your 24/7 support with all different kind of SLAs and things like that. Currently, we support like we are like a winner of multiple large scale like small business grants, and we make these solutions based on these grants and market these products for high performance computing and AI applications with commercial support. We are a silver ISV member of the OpenPower consortium. So some of the examples of customer engagements that we have is as follows. So I don't know how many of you guys are familiar with the Lawrence Livermore National Labs. So it is one of the premier research institutions in the US, responsible for the stewardship of the nuclear stockpile in the United States. So we provide commercial support for over 20 supercomputing systems, accounting for more than 11,000 compute nodes and 400,000 cores and all of their users. We also provide support for the KISTI supercomputing center in South Korea for their Neurion system with over like 500,000 cores and their various HPC applications and end users. So this is like a high level overview of the kind of commercial support that we offer. So we have like different levels of support, like a bronze level, a silver level, and a gold level. And these are the details of what is, let's say, what is entailed in each level of support. Okay, so for more details, please feel free to contact us. Okay, so that's kind of the introductory and marketing spiel that we typically give. Now, let me get into more of the technical stuff, which I hope you guys are interested in. So we have multiple products from the Xscale side. One is meant for high performance computing called Xscale HPC, which provides optimized solutions for HPC applications. Xscale AI, which is meant to provide optimized solutions as well as introspection support for deep learning and machine learning applications. And finally, MVAPIC2 DPU, which is particularly meant for accelerating applications with the new NVIDIA DPUs. Okay. And I'll go into more details about each one of these products in the next few minutes. So what is the Xscale HPC package? So the Xscale HPC package offers scalable solutions based on OSU's MVAPIC library. So these are like out of the box solutions, which means that you take it, you install it, and that's about it. You don't have to worry about anything else. And again, you might have a question, okay, why do I really need to worry about things? So the long and short of it is this. If you look at a software library as complicated as a message passing interface implementation, it could have anywhere between 600 to 1,000 different tuning knobs, which you can, let's say, play around with to get the best possible solution on like a particular architecture. And these tuning knobs could vary based on the kind of underlying hardware. For instance, if you have an OpenPower versus an Intel x86, your tuning may vary because the OpenPower architecture provides you a lot of different features that the Intel architecture does not. Similarly, if you have an InfiniBand versus like an OmniPath. Like you need different kind of tuning there. So we take care of all of these things, and we provide like an out-of-the-box solution for end customers for both CPU-based as well as GPU-based applications. Okay. So what is the upshot of all of this? The basic upshot is that you get very good performance for internode device-to-device or host-to-host communication. So typically, what is the modus operandi for moving data from a device to a remote device? So if you look at it, the typical modus operandi would be copy the data using CUDA memcopy from device to host, send the data to the remote host, and copy it back using CUDA memcopy, right? Fairly straightforward, but not very high performant. Now, why do I say it is not very high performant? Let me ask like a question to you guys. Can you guess the number of different paths available to move data from GPU on one node to GPU on a different node through like a network fabric? Like a ballpark guess, anybody? You guys are still with me, awake? Okay. So
Satyanandan, you have any answer for this? Professor Satyanandan? Okay, I think go ahead, Hari.
That's okay.
So yeah, there is a drop in my internet, so I signal. Anyways, yeah, so there are various ways of doing it actually. So you can have unified memory, and now problems are solved using unified memory. So that particular thing is actually gone nowadays. If people are using unified memory access, yes.
So thank you, Satya, for that answer. But the thing is, even with unified memory, at the end of the day, the driver has to move the data. Okay. And if you look at unified memory, the driver currently still uses something similar to a CUDA memcopy to move the data in a transparent fashion between device to host or host to device. If you compare that to more advanced schemes like a loopback based transfer or transfer using GDR copy or GPU direct RDMA, that would still be much, much, much better. So while unified memory does give you a layer of portability and let's say hide some of the complexities, it still does not give you the best possible performance. So there are 16 different options to move the data from device on one node to device on another node.
Sure.
So if you use the correct paths, then you will get almost let's say 0.8 to 1.8 microseconds for intra-node device-to-device transfers to inter-node device-to-device transfers. And that's what we are trying to highlight here. So all of these logic, the logic as which of the 16 different paths to take between from device on one node to device on a different node is taken care of by the underlying runtime, so that you as an application developer don't have to worry about like the complexities of the underlying hardware architecture. The middleware takes care of it. So you just say send and receive, and the middleware takes care of taking the appropriate path from the sender to the receiver end. Now, what is the end result of all of this optimization? So that is what we are trying to highlight here in this slide. So this is kind of shows the performance of AllReduce at scale on the Oak Ridge Summit supercomputing system, which is an IBM open power system, like a Power 9 system with NVIDIA V100 GPUs. So here we are comparing the performance of nickel versus GDR. So we can see that we are able to significantly outperform nickel for the small, medium, and very large message ranges. And here we show the 128 megabyte message range, which is typically what is used by the distributed data parallel deep learning method inside TensorFlow. Okay, so we are able to deliver very good performance and scalability. And we also have advanced solutions to use the GPU. The GPU is an extremely powerful device. Okay, only a fraction of its capabilities are currently being used. So what we are trying to do here is we are trying to see if we can take advantage of the massive capabilities of the GPUs to accelerate certain high value operations that the MPI library performs, for instance, like data type operations. Now, why are data types so important? If you look at typical benchmarks, which move data from A to B and measure just the communication time, they use contiguous data, which is contiguous in memory. But if you look at scientific applications, they would use structures, vectors, and more complicated data types, which are laid out in a non-contiguous fashion in memory. So in order to move this data, you have to pack them into a contiguous location, send it out of the network, and unpack them at the receiver side. So by doing this on the GPU itself, we are able to significantly enhance the performance. So in brief, these are the optimizations that the Xscale HPC package offers you to get out of the box fine-tuned performance on various kind of CPU, GPU, and hybrid CPU, GPU clusters. Now with that, let me move on to the next portion of the talk, which is Xscale AI. And folks, feel free to interrupt me if you have any questions, okay? I can keep talking like this forever, and which would probably be very boring for you.
Hari,
yes.
Yeah, okay, go ahead.
Go ahead, Satya, go ahead.
Yeah, so just one, this thing, like how is it basically different? Of course, I know you have been using MPVish and all, but how is it different from the concept which Mesh TensorFlow uses nowadays?
So there are two different implementations, basically. The devil is kind of in the details, so to speak. So if you look at TensorFlow currently, you have the higher level framework, which kind of is the abstraction for the applications. If you want to train a model using TensorFlow, the TensorFlow is an abstraction. But below that, you have several communication frameworks which are there to kind of move the data around. So one of these communication frameworks or abstractions is called Horovod, and Horovod can either use MPI or Nickel underneath to move the data. So here we are, yes.
Yeah, so the Horovod thing is fine. I was just trying to ask you about Mesh TensorFlow. Mesh TensorFlow is a new thing which the TensorFlow people have released for distributed deep learning itself. So I was just wondering, because I'm working on distributed deep learning with Horovod, and then we were trying to do something on Mesh TensorFlow. There's basically a mesh network. That's what the TensorFlow people have suggested it to be like. So any idea on that actually? Like how is it different from what you are trying to do on this, basically Nickel and MPVish?
So at the end of the day, Mesh TensorFlow also needs a communication substrate. And I believe they would still go over Nickel or MPI, but I can double check and I can get back to you. Is that okay?
Thank you, Hari. No issues. I just was trying to ask you something on that because I'm trying to do something on that.
Sure.
So that's the reason. Yeah. Thanks a lot.
Sure, definitely.
No I'll be in touch.
I'll be more than happy to follow up.
Yeah. Thank you so much. I'll be in touch because I am working on that. So we will discuss offline as well. Yeah.
Definitely, Satya. Thank you. My pleasure.
Bye-bye. Yeah. Thanks.
Yeah. So going over to Xscale AI. So the goal here is to have high performance solutions for distributed training for your complex AI problems on modern HPC platforms. So some of the major features are obviously easy to use and deploy. So one-click deployment, high performance, scalability, and introspection capability. Okay, so why is introspection so important? One of the most common questions that you get as a developer of a middleware is, hey, where is my performance going? You know, when I ran this application yesterday, I got this performance, but today I'm not getting that performance. So what is happening to my application? Where is my time being spent? So that visibility is what this deep introspect solution provides end customers. These are some of the high-level features of the Xscale AI solution. So it is basically powered by the MBAPICH GDR package, and it has excellent performance and scalability, and it has been directly integrated with various deep learning frameworks like TensorFlow, PyTorch, MXNet, and others. It also has an integrated profiling and introspection support with Deep Introspect, which provides a cross-stack performance analysis capability in a visual manner. And there's obviously, just like the Xscale HPC package, it has been tuned for various CPU as well as GPU-based HPC systems. So it's like out-of-the-box installation. You don't have to spend days or hours trying to figure out what the dependencies are and trying to install them at the right locations. So it makes life significantly easier for the customer. So that's on the productivity side. So what is it on the performance side? So this is like a standard comparison, comparing your basic Horovod middleware and Xscale AI middleware for distributed PyTorch training. So this was running on 8 NVIDIA Tesla V100 systems with 2 Intel Xeon like Cascade Lake CPUs, and this is the hardware configuration of that particular system. So what we can see is that as the scale increases, even from small scale to the to like 16 nodes, we are able to consistently provide improvements in performance over the standard horawatt that gets shipped with PyTorch or what you download from the website. So just by using this, you get 35% improvement in performance out of the box on like small or to like very large systems. Okay. So this is another example where we are trying to compare the performance of training ResNet 50 model on the ImageNet dataset using up to 16 GPUs. So here we are using like 4 nodes with 4 GPUs per node. So in the previous, we were using 2 nodes with 8 GPUs per node. So we are just trying to highlight different kind of like configurations representing different like deployment scenarios. So here again, we see that the Xscale AI package is able to outperform the standard implementation by like a significant margin. So same hardware, different software, significant difference in performance. So this is like the same thing with the different examples. So here we are just trying to vary the number of nodes and the number of GPUs per node from a very dense GPU system to a GPU system which is not so dense. So like from an 8 GPU per node to a 2 GPU per node. And here also you see that as the communication, the internode communication becomes more dominant, the kind of benefits and performance you get also like continues to increase here. So with more dominant internode communication happening, the Xscale AI package significantly outperforms the like the standard solution. So this is a fourth system configuration here. So this is 1 node and 4 GPUs per node. So here the main difference is that on all the previous cases we were using V100s. So here it is an A100 or the Ampere GPU from NVIDIA, so which is much more capable. And we are comparing the performance of training ResNet 50 on a synthetic data set using 4 GPUs per node on a single node. So here again, even on 1 node, the use of the right software package is able to significantly improve the performance of your training operation. So that's what we want to highlight here. So finally, let me show you how we use the Xscale AI deep introspect graphical user interface. So this is the kind of like user interface it provides. And let me tell you why we are, let's say, highlighting all reduce. For most distributed data parallel deep learning solutions, all reduce is the one and only communication primitive that is important. Why? Because at the end of each training step, you need to kind of aggregate your gradients. So what does gradient aggregation mean at a high level? So for your typical image recognition cases, so what you do is you have a large data set and you give this data set to chunk it up and give it to different people, okay, or different computers. Now suppose that you have a bunch of images of dogs, okay. Now suppose you gave system 1 images of all German shepherds. System 2 got images of all like smaller dogs like Chihuahuas, okay. Now at the end of training, system 1 knows that a German shepherd is a dog, but it does not know that a Chihuahua is also a dog. So the learning that happened on image 1, on system 1 and system 2 needs to be exchanged. And at the end of the training epoch, both systems need to realize that both a German shepherd and a Chihuahua are dogs. So that process is called gradient aggregation, and that is where you use all reduce. So all reduce is a very, very critical operation. And that's why we are kind of highlighting that particular operation here and trying to demonstrate where exactly the time was being spent for the all reduce, how much message was being used, and things like that. So this kind of gives you insights into what is going on at the application level. Now, what is the upshot of all of these things using a deep introspect? So using this deep introspect, we can potentially understand that your application is probably not using the right message size, which the middleware has been optimized to support. So you can do like a lot of specific tuning using that. And this is the kind of benefit that you get with and without the tuning solution. So once you're able to understand what is going on, you can tune your runs and get significant improvements in your overall application execution time, bringing your execution time or your scalability close to ideal scaling. Okay. Of course, we will not be able to reach ideal scaling because of communication overheads, but we are pretty darn close to it. So this is a different example of the kind of tuning that we can get. So this is the expected or the ideal use case. This was the number of images per second. So this is kind of a throughput that we use to like, let's say, quantify our training performance. Okay. So this was the kind of performance we got before tuning. And this is the kind of performance that we are getting after we are able to tune. We also have like a solution called scalable checkpointing and restarting. So for most applications, they will run for a long period of time, right? You might want to take a pause and say that, hey, I'm taking a pause right now. Let me stop here and then come back later and restart my training. So at that point, you want to store the state of your current application in some place. And this operation is called checkpointing, and restarting is called restart. Okay. So in order to perform this, you have a lot of file system interaction and a significant amount of overhead. So here we are trying to propose a solution called scalable checkpoint and restart, which is able to significantly reduce your checkpoint and restart overhead and allowing you to kind of stage your training in different, let's say, time intervals. So with your proposed solution, your overhead for checkpointing and restarting is significantly lower compared to your native solution. Okay. So in cases where you want to like take a pause and come back later, or let's say you are running on a shared system and you did not get an allocation for a long enough period of time, you had to chunk it up. So in those cases, you can use these kind of solutions and save your work and restart from that at a later point in time. Okay. So finally, let me talk about the DPU package. Okay. What is a DPU? A DPU from NVIDIA is what is called as the data processing unit. So it is like a secretary. Okay. Now you have a lot of executives out there, like a CEO and a CTO, things like that. But for all of these folks, you would have certain people allocated to them to take care of certain mundane tasks. So if you think of your processor as a CEO and the DPU as a secretary, that is kind of a good analogy. Now, what does the DPU offload? So in general, the DPU is a data processing unit, which is resident on the network interface adapter. It has certain CPU cores, like a small ARM CPU cores on it, which can orchestrate certain operations. It could be IO, it could be communication, it could be some compute. What you want to offload to your secretary depends on your choice. Okay. If you offload very, very complicated tasks to your secretary, they might find it hard. But if you offload simple tasks, like you send this, you receive this, they might be able to do it very quicker. And that period of time can be used by the executive to do more high value tasks. So here in this package, we are trying to take advantage of the low powered ARM cores on the Bluefield packages from NVIDIA/Mellanox to offload certain operations like communication orchestration and IO from the CPU, so that the CPU can perform more high value compute operations during this time. Okay. So that's a high level overview. Now we have been making several releases of this over the past few years. And one of the critical benefits is that you can get nearly 100% overlap of computation and communication and accelerate scientific applications using this. So before we head to the application level, let's start with the basic micro benchmark level. Okay. So here we are showing the performance benefits that you get with an all-to-all benchmark. So what is all-to-all? All-to-all is a benchmark where all processes talk to each other. Each process has a unique piece of data to be sent to every other process on the job. Okay, so this is kind of an all-to-all where everybody talks to everybody else. Now, this is obviously a very communication-intensive operation. And if you are able to offload some of these communication operations, then we can do more high-value compute tasks during that time. able and allowing us to, let's say, finish our overall task of compute plus communication quicker. So here we are trying to show the benefits of the DPU-based offload for an all-to-all with 32 nodes and 16 processes per node, and 32 nodes and 32 processes per node. So as we can see, we are able to reduce the overall compute plus communication time by a significant margin by offloading certain communication operations to the DPU. And in this slide, we kind of show the amount of overlap of compute and communication we are able to achieve. Where here we compare the default version without the offload capability and the enhanced version from Xscale with the offload capability. So we see that the enhanced version has near 100% overlap of computation and communication, which means that all the time when the DPU was doing communication, the CPU was doing some computation. So there is a significant benefit here. This is like a similar example with an all-gather benchmark. So in the all-to-all, if you remember, every process had a unique piece of data to be sent to every other process. In all-gather, every process has the same piece of data to be sent to every other process. So it's much less dense in terms of communication. So we get, again, significant benefits in terms of overall execution time with 16 nodes and different processes per node. And similarly, the overlap percentage you get is almost like very close to 100% here. Okay. This is what is called as a broadcast. It is another kind of collective communication operation where a lot of processes try to work together with each other. So in a broadcast, one process has the same piece of data to be sent to all other processes in the job. Okay. So here we again first compare the overall execution time, the compute plus communication time, and show how overlapping computation communication is able to significantly bring down the execution time at 32 nodes with 1 process per node and 16 processes per node. And later we also show the kind of overlap that we are able to get. So as we can see, we are able to get significant higher overlap with the DPU-based solution as opposed to the basic host-based solution. So all of this is well and good, but what is the real upshot of all of this? Is there any real benefit at the application level? So that's what we are trying to compare here. So far we were looking at benchmarks, which was looking at pure communication or a synthetic version of communication plus computation. Here we are looking at an application called P3D FFT. It's a kernel that does 3-dimensional fast Fourier transforms. A fast Fourier transform is something that is very commonly used in scientific applications like numerical simulation applications and a bunch of others to perform like, let's say, partial differential equations. Or if you want to solve partial differential equations, that is one common use for these FFTs. Okay. Now, here we are trying to compare the performance of the red line, which is the default solution, and the green line, which is basically the solution which is offloaded to the DPU. So through all of this solution, we are able to significantly reduce the overall execution time by offloading necessary communication components onto the DPU. So that's what we want to highlight here. So to wrap up, what did we do as part of MBAPISH to DPU? Vendors like NVIDIA and Mellanox came up with more smarter network interface adapters, which are capable of offloading higher value tasks from the CPU. We took these DPUs and tried to create a software framework which was able to use the DPUs and the CPUs in a unified fashion and was able to offload certain operations from the CPU to the DPU so the CPU could do something else. And as a result, we were able to accelerate the overall application by a good margin. So this is again 18% benefits at the application level, which is significant. Okay. So with this, I kind of come to the end of my brief presentation. I'm happy to take any questions if you guys have. If not, I can hand over to the next panelist. Thank you.
Hari, thank you for the wonderful presentation about the Xscale offerings, especially the distributed deep learning. and hopefully, some of the people from this group, would like to see that demo also. We will see how we can show it, using our Sastra system, which we
Sure.
said recently. Thank you
So,
once again. And Professor Ilango and Gabriel, any questions on this distributed deep learning, the Xscale solution from Ohio State?
so looks like one of the attendees, Anupama, has raised her hand. Anupama, do you have a question?
Anupama, okay, let me allow her to talk. We do have
Yeah.
some time. Yeah. Anupama, please go ahead. Anupama?
Probably that was a mistake. It's okay.
I'm Dr. Ilango here. I have a few questions. Dr. Hari, you said that PyTorch was used here for high performance computing. Was it coded by using PyTorch, or it is been used any other along with library, TensorFlow or something?
So we have used, thank you for the question, Dr. Ilangovan. So we have used both PyTorch as well as TensorFlow in our experiments. So in general, what we see is that in the academic community, PyTorch is gaining more traction because it's much more easier to use. But in the industrial setting for companies and all, it's still mostly TensorFlow, like by and far. So we are just trying to show like a couple of examples using both TensorFlow and PyTorch.
Thank you, Doctor.
Thank you. If there are no other questions, then I can hand over to the next panelist.